All right, I'm going to do my best to explain this, and then if there's any questions you have left, please come ask me. So the first thing I did was I went through and actually plot and graphed this function by plugging in different values for theta that we know from the unit circle. So for example, if you plug in 0 to the r function, this is r. If you plug in 0 to the function r, you get 3. If you plug in pi over 6, you get 1 plus radical 3, which is approximately 2.78. And I'm just plotting them on the polar coordinates. So at 0, we had 3, that's this point. Then at pi over 6, we plot a point out here, that's at 2. So on and so forth. And I just started plotting these points, and I was able to see that way how the function was being plotted. But then also I can see in my chart how at 2 pi over 3, that was the first time that it equaled 0, and then it went around inside this little inner circle right here, and then it came back to 0 again at 4 pi over 3, which just went to show that those were the same values I found when I set it equal to 0, 2 pi over 3 and 4 pi over 3. So if you kind of look at how it's formed, it starts here at 0 radians, and then it continues over here, and you can see that the top half of it goes to about there. So from 0 to 2 pi over 3 is the top half of this function. And it's a symmetric function. It's symmetric about the polar axis right here. So that means this bottom half right here has as much area as the top does. So if you can find the area of the top half, then you can just double it in order to get the area of the bottom half. And that would give you the area of the outside ring. So that's kind of what we have here, right? So the area would be, this is the formula for the area. So from 0 to 2 pi over 3, which is, again, from 0 radians all the way to 2 pi over 3. That was the first time it equaled 0. That's the top half. So the integral from 0 to 2 pi over 3 of r squared times 1/2. That's just the formula for area. And I'm multiplying it by 2 to account for the symmetry. So that first area just gives me the top half. If you multiply by 2, it gives me the bottom half. Then, if you find the area of the inside circle, it would be 1/2 times the integral from. So for the inside circle, this one is 2 pi over 3, and then it keeps going. But again, let's just look at half of it. So if I can just find the area of the top half of it, then I will be able to calculate just by doubling again what the area of the bottom half is. So this one was 2 pi over 3, and then this was 3 pi over 4. This one right here was 5 pi over 6, and then right here we have pi. So at pi, it lands back on the polar axis again. So pi, and then this one was 7 pi over 6, and then 4 pi over 3 again. So if I can integrate from pi to 4 pi over 3, then I can find out the area of just that little inner top half of the loop, and I can double it to get the area of the bottom. So from pi to 4 pi over 3, the integral there will give me the area of the top half. So if we integrate from pi to 4 pi over 3, of r squared d theta, and multiply all of that by 2 to account for the symmetry, that'll give me the inside loop. So if you put that in your calculator and put that in your calculator and subtract them, it should give you the value that was in the Master Math Mentor book. And so you asked earlier how to find those limits of integration. So set them equal to 0 to figure out where they both intersect right here, but then just kind of divide them into halves. And I think the easiest way is probably to get your mind around it is to graph some of the points to kind of see where things are lining up and how to graph them in polar. So like I said, if you have more questions about that, please let me know, but I hope that that's at least a general introduction to what you needed to get.